Okay, now that we know that thermodynamics is really just a continuation of conservation of energy, but specifically looking at internal energy, let's see where that goes with gases and in terms of what's going on exactly there for internal energy. Well, there's three things that were kind of discovered earlier on in science, and that was if we had a mass of gas that was constant. So notice here the mass is remaining constant for the gas. We're not talking about the masses on top here. We're talking about the mass of the gas. The system is the gas. And when the temperature is constant, so notice over here the temperature is constant. If we increase the pressure um, on the system, on the gas, that will decrease its volume. So we find out that these are inversely related. Let's repeat the experiment, but this time let's keep the mass constant again, but let's keep the pressure constant. So notice this pressure is constant. We have the weights up here on top of the gas being constant. In that case, all we're doing is we're changing the temperature, and as the temperature increases, the volume of the gas, it expands, increases. So that's a direct relationship. And then one more experiment, and this one will keep the mass constant. So you'll see there's so many particles in here. And this is a closed container, so the volume is constant as well. And when we heat up those particles, the temperature is going to increase, and as the temperature increases, the pressure increases. And hopefully the can doesn't explode on us. So that's a direct relationship. We're going to combine those three relationships into what's called the combined gas law. PV over T is some constant. P in this case is the absolute pressure in pascals, V is the volume in cubic meters, and T is the absolute temperature in kelvins. If you know the temperature in Celsius, if you add 273 to it, that would be the temperature in Kelvin. So for instance, 0 degrees Celsius would be 273 degrees Kelvin. 100 degrees Celsius would be 373 degrees Kelvin. The absolute pressure of a gas triples as its volume doubles. If the initial temperature is 20 degrees Celsius, what is the final temperature? So let's try this example here. Okay, first of all, one problem here is the temperature is in degrees Celsius. We need to convert that into Kelvin. So 20 degrees Celsius would be 293 Kelvin. Okay, so we're going to use P1V1 over T1 is going to be equal to P2V2 over T2. It's constant. So we know the pressure and volume at first, and then later on the pressure triples and the volume doubles, and we're trying to figure out what that new temperature is, T. The original temperature was 293 Kelvin, or 20 degrees Celsius. Okay, so I can rearrange and solve this for temperature. The P and V cancels, and it's going to be 6 times 293 Kelvin, or 1758 Kelvin. If you want to figure out how many degrees Celsius that is, you would just simply subtract 273 from it. What volume does 1 mole of an ideal gas at STP occupy? Well, we saw that P1V1 over T1 equals some constant. Well, that constant is N times R, where N is the number of moles and R is the gas constant. So in this case, it's 1 mole. The gas constant is 8.31 joules per mole per Kelvin times 273 Kelvin. And solve for volume, we get 0.0224 cubic meters. And if you want to know how many liters that is, that's 22.4 liters. So looking at what's going on here, if you're trying to figure out, what exactly is happening when you change the temperature. Well, when you change the temperature of something, you're actually changing the kinetic energy of the particles. Well, the kinetic energy particles, that means the particles are moving. Those particles are confined and they hit the container that they're confined in. that hitting would exert a force, and that force is over a certain area, so we have a pressure. So we could think of the average force of those particles in the x direction would be the change in momentum over change in time. And again, change in momentum would be mvx minus negative mvx. Now the reason that's true is because this is an elastic collision. The speed's going to be the same afterwards. And so the change in momentum will be 2 mvx. L is the length of the container, so 2L would be equal to the distance that it travels in a certain time, delta t, using kinematics, d equals v bar t. So we can plug some of the stuff that we know in here. So we could solve for delta t. Delta t is going to be 2L over Vx. And of course we have the 2mVx on top. And simplifying, we get mv squared, or mvx squared over L. So we just figured out what the force is as a function of the mass of the particles and the speed of the particles and the container's dimensions itself. Now keep in mind that we've got lots and lots of different particles in there, so we'd have to multiply it by the sum of all those speeds squared. And really it could have any of those speeds, so we need to figure out what the average of that is. Now one more thing, that's just in the x direction. This is a volume, so there's 3 degrees of freedom in this case. Could move in the x direction, could move in the y direction, could move in the z direction. So I have to really multiply that by 3 to figure out what the net force is. And this big N came from how many particles we're dealing with here. So if it's just one particle, it'd be, m here. But if we have n particles, we're going to have a much bigger force. So rearranging this, solving for a force, we have n over 3, the number of particles over 3, times the mass of a particle divided by the length of the container, times the average of the speed squared. If I divide that by the area of one of the sides of the container, and I have to do this to both sides, I know already that force divided by area is pressure. And I know on the other side length times area, so length times area is the volume. I'm going to multiply both sides by V, and I get PV equals the number of particles divided by 3 times the average speed squared. And so this gives me one of the ideal gas laws. PV equals N times the Stefan-Boltzmann constant times the temperature. So we can see that it's kind of related to the temperature here. And I can plug that in for PV. Oops, let me go back. And I can plug that into PV, and I find out that Stefan-Boltzmann constant times the number of particles times the temperature is related to the average kinetic energy. It's kind of related to this average kinetic energy of the particles. So temperature is really related to the average kinetic energy of the particles. So there's 2 forms of my ideal gas law. PV equals nRT, where R is the universal gas constant, 8.31 times, 8.31 joules per mole Kelvin. Or you might see it in a different form, PV equals KNT, where K is the Boltzmann constant, 1.38 times 10 to the negative 23rd joules per Kelvin, and N is the number of molecules. So if you know the number of molecules, you need to use one with Stefan-Boltzmann constant, whereas if you know the number of moles, you're going to have to use PV equals nRT. And again, the number of particles or molecules in 1 mole is 6.022 times 10 to the 23rd particles. That's Avogadro's number. Okay, going back to this idea that NKT equals N over 3 times M average speed squared. Rearranging this slightly and canceling out the ends on both sides, the number of particles, we get 3kt equals m, the average speed squared. You'll notice on the right hand side that looks very similar to kinetic energy. So I'm going to multiply both sides by 1/2, I think, here somewhere. Oh, in a second I will. Solving for the average speed squared, I get this, and so I needed to find this new term that I'm calling root mean square speed. That's what the RMS stands for, is equal to the square root of the average speed squared. So whenever you see a VRMS, that means for root mean square speed, and the way you calculate it is first you square the speeds, then you find the mean, the average, and then finally you take the square root. And that will be equal to the square root of the quantity 3 times the Boltzmann constant times the absolute temperature in kelvins divided by the mass. Going back to this idea though of 3kt equals m average speed squared, you notice if I multiply by half I'll have kinetic energy. I'm going to multiply both sides by half. So now I have 3 halves kt on the left hand side. Now I'm going to go ahead and multiply both sides by the number of particles n, and this kt we saw on the prior screen. We saw that it was given in, it's also equal to n times r, so I'm going to substitute that in. And really what this is internal energy of the particles. Again, it's related to the speed of those particles. So remember the very first PowerPoint we saw that this plane crashed and its temperature changed. Well, why does temperature change? It's because those particles are vibrating faster. So its internal energy of its particles is greater. If I wanted to figure out the change in internal energy of a monatomic gas, which has 3 degrees of freedom, that's going to be given by 3 halves nRT. That's the internal energy. Okay, going back to the root mean square speed, what is it exactly? Well, here's a graph of some particles. This is the animation. I'm not going to go to it right now, but it shows these particles. If you go to this animation, you click on it, and you'll see these particles kind of bouncing around in here, and they're elastic collisions, and these are point particles, so they never collide with one another. If you look at a distribution of their speeds, it'll look kind of like this. Here's the average speed here, or this is the high. This is the this is the kind of the particles, the most common speed, I guess. This one, VP. Then we have the average speed, and then we have the root mean square speed, which is related to the kinetic energy of the particles. That speed of root mean square speed is also related to the temperature, and so it is close to the average speed, but it's not exactly the same. Let's do a few examples with root mean square speed. So let's say we have the following speeds: 3, 5, 1, 8, 9, and 0, and we want to figure out the mean and the root mean speed. Again, remember, root mean speed is going to be related to the temperature and also to the internal energy of the particles. Well, the way you find the mean speed is pretty simple. You add them all up and divide by the number, which in this case there were 6 of them, and we get 4.3 meters per second. Now let's find the root mean square speed. First thing we have to do is square them, then we find the average, and then we take the square root. So you'll notice that first we're squaring, then we're adding them all up and dividing by 6 to find the average, and then finally we're taking square root, and we get 5.5 meters per second. The 4.3 is not related to the internal energy. It's not related to the temperature. It's the 5.5 that's related to the internal energy and the temperature. Let's look at another example. What is the root mean square speed of helium atoms near the sun, where the temperature is 6,000 Kelvin? Root mean square speed is going to be given by the square root of 3kt over m. Okay, so plugging in the Boltzmann constant, and the mass of helium and the temperature. The mass of helium, an alpha particle is 4U times 1.6 times 10 to the negative 27 kilograms per U. So solving, we get 6,120 meters per second, or 13,700 miles per hour. So that's how fast those particles of helium are moving on the sun's surface. Okay, let's look at another example. What's the root mean square speed of a nitrogen N2 molecule in this classroom, or in your home in your room at home? Again, the temperature is going to be about 20 degrees Celsius at home probably, or even here at school. We have to change that into Kelvin though, so that'd be 293 Kelvin. We have to look up what the mass of nitrogen is, and I'm trying to remember, I think it's 14 grams if it's monatomic, but this is diatomic, so I believe that's 28. So it's going to be 28U times that conversion factor for U. So that would be given as the following. And so we get 510 meters per second. So those particles, the root mean square speed, which is related to the temperature and the energy of the nitrogen particles, is 510 meters per second.